Alright, so Felix Wunsch from Carlsberg Institute of Technology, talking about his implementation of 802.15.4, which is, that's Bluetooth, or is it Zigbee? I always forget what these numbers mean anymore. Well, you know what's Zigbee, okay. This is great. Felix is one of our first Google Summer of Code students who's continuing to do some stuff for us.
Thank you for the introduction. My name is Felix Wunsch. I'm with the KIT in Karlsruhe in Germany. And today I'm going to talk about gr-ieee802-15-4, which is a flexible IEEE802-15-4 testbed for GNU Radio. The outline for my talk is pretty straightforward. After a few motivational words, I'll go into the IEEE802-15-4 standard and explain how it works. And then proceed with the gr-ieee802-15-4 radio module, how it's designed, and what it's capable of. At the end, there will, of course, be a short conclusion. So, as we are in the Internet of Things, over the last years, it's been a trend that more and more wireless connectivity to all kinds of devices, be it sensors or just things, as in the Internet of Things. This has given rise to a whole load of new possible applications in a multitude of areas. In 2011, the German government launched a large research project called Industry 4.0, and the central vision of this project is the so-called smart factory. In a smart factory, just everything is smart. Logistics are smart, maintenance is smart, and of course, products are smart. Which is to be achieved by this is, as always, increased productivity with increased efficiency and increased flexibility. In 2011, however, this was just a mere vision put down on paper. Since then, research groups have assembled and discussed and debated how to put this vision into reality and which requirements there are, which components are needed, which components already exist, which can be modified, or which have to be developed first. And when it comes to developing and testing wireless communication algorithms, what would be better suited than a software-defined radio approach? It allows rapid prototyping and field tests while maintaining easy modification of components and short development cycles. That's, of course, the point where GNU Radio, and specifically in this case gr-ieee802-15-4 comes in. Regarding industrial wireless communication standards, there's already a quite great number to choose from. I put the logos of some of them on the slide. Surely all of you know Zigbee. Many will know wireless HART, which is the wireless version of the wired HART protocol, and the ISA has quite recently, I think in 2011, released a standard called 100.11a. All these standards and more have one thing in common. They are all based on IEEE802.15.4. And this is also the reason why it makes so much sense to have a GNU Radio module that can speak this standard. And it's also the reason why we're now going to have a deeper look at IEEE802.15.4. So, the standard defines the lower two layers of the OSU model, which is the PHY and the MAC. Depending upon your application and region, there are different modes for different modulation schemes, frequency bands, and data rates available. And undeniably the most popular one that is connected with Zigbee is the OQPSK PHY, which operates with a 2.4 GHz XM band and offers 250 kilobits per second. There's a whole lot of available PHY layers, as I said, and I put them down in this table here. And when I had a look at this PHY layers, one thing struck me. And if you have a close look at this table, you'll notice that there's only two PHY layers that operate in the same frequency band and offer the same data rate. That's the OQPSK PHY I mentioned earlier, and the CSS PHY, which stands for Chirp Spread Spectrum. That got me curious, and in the end I decided to implement it and add it to this radio module. So let's have a look at the PHY layer. Let's start with the OQPSK PHY. The OQPSK PHY is actually a direct sequence spread spectrum system where the chips are OQPSK modulated. The frame, a PHY frame, which is also called a PHY protocol data unit or PPDU, has a pretty simple structure. At the beginning, there's a synchronization header with a preamble and a start frame delimiter. Then comes the PHY header, which tells us how long the payload is, and at the end there's of course the payload. The modulator is also relatively simple. We take the binary data from the PPDU, we take 4 bits, group them, form a decimal index from 0 to 15, take this index and choose a spreading sequence, which is 32 chips long. And this stream of chips is then modulated with OQPSK PHY. If you look into the standard, let's continue with the CSS PHY. As I said, it stands for chirps per spectrum, and it's a relatively recent addition to the standard since 2007. It's pretty wideband and has a high resilience against Doppler shifts. For comparison, the OQPSK PHY has a baseband sample rate of 4 megasamples per second, whereas the CSS PHY is 32 megasamples per second. On the other hand, with the CSS PHY, you can have up to 4 users in the same band at the same time, because it uses 4 approximately orthogonal sets of frequency ramps, chirps, for the user separation. Each of these frequency ramps is weighted with EQPSK symbols, which then convey the actual information. The frame structure is very similar to the OQPSK PHY, which is why I want to go further into this at this point. And in contrast to the OQPSK PHY, we have 2 possible data rates with 250 kilobits per second, just like the OQPSK PHY, and 1 mbit per second. The change in data rate is not achieved by changing the bandwidth, by changing the spreading spectrum. So if you have a look into the standard documents, you'll find this reference modulator. And it works as follows. You take the PHY header and the PSDU bits, so the payload and the PHY header, which tells us how long it is. You go into this demultiplexer that alternatingly assigns the bits to I in Q branch. Then you have the symbol mapper that similarly works to the OQPSK PHY. That means we take, I think, 6 bits, form them into a decimal index, and choose a spreading sequence. If we use the slower mode, with 250 kilobits per second, we also have an interleaver that interleaves the chips additionally. And before we go into the QPSK mapper, frame generation happens. The synchronization header, which consists of preamble and start frame delimiter, is already pre-coded and chosen depending upon the data rate. So if you choose 1 mbit per second, you'll have a different synchronization header than when you take 250 kilobits per second. After the QPSK mapper, the symbols are differentially encoded and they become the QPSK. The last step is the multiplication with the subchirp, so the chirp sequence which come out of the chirp sequence key generator. And at the end, you get a modulation scheme that is called differential quadrature chirp shift key. After all this talk about frequency ramps and chirps, I'd like to show you how they look in the frequency plane. Here with 4 of them, 1 for every user, 1, 2, 3, 4. And you can see this is 1 chirp set. Consists of 4 so-called subchirps. And each of these subchirps is weighted with 1 DQPSK symbol. If you now compare the chirp sets of the different users, you'll notice that the frequency ramps never share the same subband, the higher or lower, or at least have opposite direction. That's what makes them separable in the end. To further lower the cross correlation between the user's chirp sequences, there's also these user-specific time gaps. Okay, enough about the PHY. Let's have a look at the MAC layer. The MAC layer basically has 2 modes. There's a beacon-enabled or slotted mode and a non-beacon-enabled mode, which is called unslotted. Both variants have in common that they use some variant of CSM-ACA, which stands for Carrier Sense Multiple Access with Collision Avoidance. That's basically some kind of listen to for talk algorithm, and also what Wi-Fi does. In a non-beacon enabled mode, which is also the simplest mode, devices are not synchronized. They just, whenever they have to send the data, they use CSMACA, and when they get a kit sent, they just send it. In the beacon enabled mode, however, devices are synchronized in so-called super frames. And these frames, in turn, are divided into time slots, and some of these time slots can be exclusively assigned to devices. This is also the only mechanism the standard offers to ensure the deterministic latency and therefore some kind of quality of service. And it's commonly regarded as a weak point for standard. How do the super frames look? Well, they are surrounded by beacons, and between those beacons lies the active portion where all the action happens, and the inactive portion where nothing happens. That's especially beneficial if you have a battery-powered sensor device with a low duty cycle, because during this inactive portion it can enter a low-power sleep state and just conserve energy. In the active portion, you have the contention access period, where a slotted version of the CSMACA algorithm is applied, and the contention free period, where the exclusively assigned guaranteed time slots reside. Okay, now that you know more or less how IEEE802-15-4 works, we'll go over to the actual GNU Radio module. It's hosted on GitHub and currently maintained by Bastian Brössel, who also maintains gr-ieee802-15-4. It's based on the initial OQPSK5 implementation of Thomas Schmidt at UCLA, and its main features or components are the OQPSK and CSS file, which are encapsulated in hierarchical blocks. We have a Mac block, and we have a block that implements RIME, which is a network layer communication stack for sensor networks. The modular design, which you will see in a second, is very close to the OC model and hopefully makes it easy to understand. And there are also complete transceiver flow graphs, so you can use it actually in some kind of plug-and-play manner. And it's also, if you use the OQPSK5, interoperable with commercial off-the-shelf sensor devices. So have a look at the top level GRC flow graph. As I said, it's pretty close to the OC model. On the bottom, you have the PHY layer. Here is the OQPSK5 in blue, the complex baseband stream in an output. Communication via to the Mac happens via message. The Mac block itself then communicates with the network layer, which is the RIME stack in this case, and the network layer then skips a few layers, and here we have the application layer, which is represented by the socket PDU block. So, how do these 5 blocks look on the inside? As I said, they are hierarchical blocks. We start with this pad source. Here's where the Mac frames come in. We have the access code prefixer, which adds the synchronization and the PHY header. Then we form the decimal indexes, choose the spreading sequences. Then here's the OQPSK modulation with interpolation, pulse shaping with a half sine wave, and that characteristic for OQPSK, we delay the Q part of the signal by half symbol time. Then here we have a burst tagger. This block adds start of burst and end of burst tags to the stream so that we can have the bursty transmission without the user P complaining about underruns. Here you can see the receive chain. What I would like to note is that except this and this block, these are all stock radio blocks. And I find it pretty amazing what you can do just by using what's there, using it intelligently and parameterizing it correctly. So now let's have a look at the CSS file block, which is a little more complex, but still follows the reference modulator we saw earlier very closely. Here, Mac frames. PHR prefixes, so that's the field that tells us how long the frame is, and the payload is. Then we have 0 padding, that's what, and we didn't see this block earlier, but that simply needed to satisfy some block boundaries. We We have a deinterleaver that assigns the bits to INQ. We choose our spreading sequences. We have an interleaver. Here, the framing, the frame generation happens by prepending the synchronization header, QPSK, differential encoding, multiplication with chirp sequences, and burst tags. Then here, on the lower half, we have our receiver. Again, here comes in the complex baseband. The multi-user chirp detector is effectively a correlator that just correlates with the desired user's chirp sequence and suppresses the others. And it also demodulates the DQPSK symbols. The causes loops, the second order, or you could also use the second order PLL, then correct remaining frequency offsets. In practice, it can correct up to 50 kilohertz, which is enough for most applications, I guess. And these two blocks perform frame timing synchronization. And once our signal has passed these blocks, they return aligned, complete frames. And from then on, it's just the modulator backwards. DQPSK becomes QPSK. We split into IQ. We drop our synchronization header. We deinterleave. We take our spreading sequences, map them back to bit sequences, interleave or multiplex the two bit streams, remove our padded zeros, remove the phi header, and here the payload remains, which is also the MAC frame, is then handed to the next layer. A few words about the MAC. There's only a very simplified version of the MAC implemented. It just adds a relative MAC header for a data frame and calculates and adds a 16-bit CFC word. There's no actual medium access algorithm. Well, why is that? Naturally, radio itself and non-real-time operating systems impose non-deterministic latencies on our system. And these are just too large to satisfy the timing requirements set by standard. For example, the maximum wait time for an acknowledgement frame is less than a millisecond, and that's not a show list requirement. Even depending on the configuration, there might be requirements on the order of a few hundred microseconds. So that's why there are no real MAC blocks. This is already time where I come to my conclusion. We can recap what we learned about gr-ieee802-15-4. It implements two phi layers, the OQPSK and the CSS phi. It contains simplified MAC and a network layer protocol. There's full GSC integration, and it's important that it follows the OSI model very closely, and I hope that it really helps in understanding and maybe extending the project. It's interoperable if you use the OQPSK phi with commercially available sensor devices. It's of course fully customizable and also easily extendable, since this year it's even GR module compatible. So if you want to contribute to this project, would be great. You could, for instance, add additional phi layers. You could play with medium access algorithms, or just add any feature you think the project will benefit from. Well, at this point, I hope you enjoyed my talk. I want to thank you for your attention, and if you have any questions, I would like to answer them.
Do we have any questions?
How many users can use that CSK, and also how far do they have to be so that there's no interference? I mean, if one is very close, one is
You mean channels or in one channel?
in one channel, say.
In one channel, you can have up to 4 users.
Okay.
Although the interference increases rather strongly if you have 4 users. 2 users is pretty easy, and it also depends which users' chirp sequences you use, because they are not equally orthogonal. So there might be better or worse choices.
Right, if one is closer and one is further, the closer one is going to use more interference, I presume, right? Is that So you're not going to get full separability, that's all, that was my question. You're not going to get, you're not going to get full separability, like you said. Yeah.
No, it's almost orthogonal, just almost.
Thank you.
My question has to do with software reuse, block reuse. I saw some familiar blocks like the Costas loop.
Yeah.
Can you describe how much effort it was and how much were brand new blocks that had never been built before and how much reuse there was?
Okay, actually I think I could have reused much more blocks than I actually did. I'm usually pretty fast at implementing blocks myself just because it's fun. But of course it's much more sensible to use existing blocks. And for instance, Costas loops are implemented. I mean, the OPP cafe is a great example how you can reuse existing blocks. Often my blocks had some special requirements that then made me implement it myself rather than diving into the source and getting the information if it is actually capable of doing what I want and so on. But if you invest some work into it, it's really possible to reuse lots of blocks. Just like, an example would be, I prepend the synchronization header in the CSS file. I could have used the vector insert block. I just didn't because actually I think at that point I didn't know it existed. Yeah, that's the only thing, but yeah.
Have you thought about changes in, like, a GNU Radio architecture that would allow you to make a working transceiver?
The core architecture. Okay, yeah, having, or say the delays or latencies that occurred, I think that's nothing Radio can do it, can solve itself because it's just like Ethernet and some interrupts that are happening in the OS. That's just something you have to live with.
I'd be curious, like on the embedded system, like the E310 or something like that, where you don't have the USB or Ethernet latency. I wonder if we could get it there.
Well, I used the CSS file mainly for simulations of bit array curves and stuff. That wasn't too bad for me, and when I simulated over the air, of course all these files also work over the air. I could adapt it so that it always works. But yeah, I didn't actually implement it on any embedded systems.
I think it'd be an interesting push, see what happened. Anything else?
One more question, I'm sorry. Last question. So I know at the same university that you're from, they do a lot in automotive radar. Are those chirps?
Can you simultaneously get ranging up or using those chirps and automated?
Actually, I think this file was thought for ranging too, but it actually never was used for that. It's admittedly pretty niche file. There has been one company, I think Germany, that kind of pushed it into the standard, and they are also the only manufacturers of chips that support this file area. Yeah.
Anything else? So I got one thing in my mind. Travis Goodspeed has his kind of famous packet injection attack against Wi-Fi, and we were hanging out one day and he was showing me on paper how he thinks he can do an injection attack against ZigBee. I don't know if he's ever actually been able to apply that in the real world, and I'd be curious what, using this type of a system we can do to test the security modes of, in this case, between ZigBee. I mean, this is the big thing, right? This is why we're at DEF CON. This is why there's the big InfoSec communities kind of took on looking at GNU radios for those types of questions. But that particular attack against ZigBee that he's got, I don't know if he's written that up yet or if he's got a paper out, but I think it'd be really cool to be able to explore attacks like that through, these now open available modules.
Yeah.
More common than anything. All right, so let's thank Felix again.